Hi, in this video I will give an update to my RISC-V FPGA project that I implemented blocks for SDRAM controller, SPI interface for SD card, and also PS2 keyboard interface. Now I can boot from SD card onto SDRAM. A good portion of this update will be on locating data sectors of a boot file on a FAT32 formatted SD card. This is the current system block diagram. In addition to implementing additional function blocks, I also reduced the processor clock to 40 MHz to have more system stability. Actually, most of the hardware I used in this update were already there on the PCB. I used this board for a project before that also had SDRAM, keyboard, SD card, and video, but I only used the CGA video block, and I rewrite the other blocks as they can be different enough. The SDRAM I have on the FPGA board is 8x8 component. For a 32-bit access, I need to use at least a burst length of 4 for sure. I spent some time tweaking the SDRAM timing, and eventually I will flop all 4 bytes from SDRAM before forwarding the word data to processor. This causes an extra cycle read penalty, but I think that's fine for now. For PS2 keyboard, there are many resources on the internet explaining how PS2 works. Actually, I started out by observing the waveform from a real PS2 keyboard, and I found this reference on the internet closest to what I need. So here's a simple block diagram of what I have right now. It contains a 4-entry FIFO for keyboard buffer. For data out from this PS2 keyboard block, I'm muxing a KB hit signal as well as using a 32-bit data width. So when I read with an empty FIFO, it will generate a all ones output. This behavior resembles KB hit and get ch functions in C language, so the software implementation is easier for now. For SD card read, I just built an SPI interface and let the software take care of the rest of the work. Again, I don't need to emulate a PC floppy controller with the SD card, but just a straight SPI interface works fine. Here are the references I used for this work. The implementation is pretty straightforward. Now that I have most of the components ready, I wanted to be able to boot from a FAT32 formatted SD card. I work mostly on PC Windows, so a FAT32 SD card is more convenient for me. So the idea is I put the boot code as a file named boot.bin on the SD card, and my boot software will look for that file, load it onto SDRAM, then jump to it. Here's a reference to FAT32 format from Microsoft. I will do a quick walkthrough of the procedure. First, the software will load sector 0 on the SD card and extract parameters as indicated here. These parameters are essential to calculate and locate the data blocks I need. According to the Microsoft documentation, there are 3 regions for FAT32. The first is the reserved and hidden sectors, including sector 0. The second is the FAT region, which can contain multiple of FAT tables. In this example, the parameter from sector 0 tells us that there are 2 FAT tables on this SD card. As for FAT32, there is no dedicated root directory region, so the third and the last region is the file and directory data region. After putting together the parameters we collected, we can calculate the starting sectors of FAT table and data region. Now we load the first sector from data region and trace for file directories. Each file directory entry is 32 byte in length. I just list the ones in an entry that's relevant for my purpose. The first is 8.3 format file name, and I look for boot.bin file name. Once it is found, then I can get the file size in byte and starting cluster number as indicated here. In this example, the file size is about 7 kilobytes and the starting cluster is 6. Next, we read in the FAT table. I think either FAT1 or 2 would work. I just use FAT1. Each word entry in the FAT table represents a data cluster, and the entry sequence represents the cluster number starting from cluster 0. However, the first two clusters are not used, as I copied the explanation from Microsoft's documentation here. The higher 4 bits of the 32-bit entry are not used to index a cluster number, but just the lower 28 bits are used. All zeros in the cluster index means the cluster is free and available. All ones in the cluster index means the current cluster chain is terminated. To find the cluster for boot.bin, we start with the 6th entry, aka cluster 6, and we get the number 7. That means the next cluster after 6 is cluster 7. Then we go to the 7th entry, and we find it to be a number that is 0 followed by 7 Fs. This terminates the current cluster chain. So boot.bin, we get cluster 6 and 7. Now we want to fetch the data cluster to read in the boot.bin file onto SDRAM. As previously stated, the first cluster starting with data region is cluster 2. So we can calculate and map clusters 6 and 7 into proper sector address. Remember, for each data cluster, we need to start with the starting sector and read 8 consecutive sectors to make a full cluster. That's about all we need to do. We'll get the starting sector of cluster 6 just to double check it's the program we put in boot.bin file. And it is. Now for the following demo, originally I wanted to do a hello world print, but then I found there is a text mode Tetris from another YouTube channel, so I just used that. I did some minor modifications so it will work on my system. I think this is more fun than just a hello world. Here's the demo. I am still using PCXT style memory check messages, and also print some debug messages during boot. Okay, that's about the demo I have. Until my next project update, thanks for watching.